Hello, friend. Good evening. So, going to start my paper reading of today. A very important paper. A head-driven algorithm for estimation upper and lower body emotion in virtual reality environments. It's really a very great paper, and it's very new paper also. It's published. You can see the date of publication is 29th of April 2025, and now it's reading this paper. You can see once again. I will show you the date. You can see the time is 9:11 and 4th of June 2026. Just 1 year back, 1 year and 1 month back, this paper was published, and really it's very great because it's really the new technology, the current technology about the current technology that is going on virtual reality environments is same and almost same. Okay, so read it carefully.
Experience,
One
expanding its
minute,
potential
1 minute.
applications across
What I can
various
do,
fields.
starting from here, a
April
head-driven.
2025, a head-driven algorithm virtual reality environments. Jimin Lee, Junghyun Kim, and Youngwon Kim School of Computer Engineering,
I can.
National Institute of Technology.
Yeah.
Gumi. Corresponding author Youngwon Kim. This work involved human subjects or animals in its research. Approval of all ethical and experimental procedures and protocols was granted by Ethics Committee for effectively estimating partial upper and lower body movements in a virtual reality environment using only head movements and synchronized head rotation axes without the need for additional hardware.
Yeah.
The proposed algorithm calculates the angle between the avatar's pelvis and the head rotation axis to naturally reproduce the user's upper body inclination and lower body bending. Notably, advantage of efficiently utilizing limited computational resources in multiplayer environments. The experiment was conducted in 2 stages. In the first stage, the objective performance of the algorithm was evaluated by comparing it with ground truth inclination data. In the second stage, participants performed 2 types of games to assess their sense of immersion and embodiment. The objective results demonstrated that the proposed algorithm accurately and naturally expressed upper and lower body movements. Additionally, post-experiment surveys indicated that participants reported a high level of immersion and a natural interaction experience. This study presents a cost-effective solution for tracking upper and lower body movements in VR environments without requiring additional hardware, significantly enhancing the immersion of the VR experience. Future research will explore the expansion of the method to include upper body rotation estimation and full body motion tracking, incorporating user locomotion.
Yeah.
Index terms avatar synchronization, virtual reality, head-mounted display, motion tracking, upper body tilt. Introduction. The advancement of virtual reality technology offers users a highly immersive experience, expanding its potential applications across various fields. Recent studies have highlighted that XR technologies, including virtual reality and augmented reality, can significantly enhance user engagement and learning outcomes across educational and industrial fields. In particular, avatar-based interactions within VR environments play a crucial role. The associate editor coordinating the review of this manuscript and approving it for publication was Lei Wei in enhancing user immersion. To further elevate immersion, factors such as the consistency of visual and proprioceptive feedback, the user's perspective, and the visual fidelity of the avatar are paramount. Additionally, research has been conducted to refine the details of the interactions between avatars and virtual environments. However, most current VR systems require external hardware such as motion capture devices or sensors to accurately track upper and lower body movements.
Yeah.
Although these devices enable more precise tracking of user movements, they also lead to increased costs, system complexity, and reduced. 25. The authors. This work is licensed under a Creative Commons Attribution 4 license. For more information, see 76006 to a broader range of users, particularly in multi-user environments. Figure 1. Comparison of user posture and the resulting movement of the virtual avatar. The user's backward posture, with the waist bending algorithm, and the resulting posture of the virtual avatar. The user's forward bent posture, and the resulting posture of the avatar, with the waist bending algorithm. Accessibility for users. Moreover, the need for immersive, real-time feedback systems in XR environments, especially without relying on complex external hardware, has been emphasized for improving practical applications such as construction safety training and industrial operations. To address these challenges, this study proposes a novel approach for estimating upper and lower body movements using only the head-mounted display, without relying on any external hardware. The key concept of this approach is to analyze the head rotation axis data and the trajectory of waist tilts gathered from the HMD to accurately reflect the avatar's movements. This method allows for the implementation of natural and consistent user actions in a VR environment without additional equipment, and is particularly advantageous in terms of resource efficiency in multi-user environments. As illustrated in Figure 1, the proposed system effectively translates user movements into corresponding avatar postures. Figure 1 compares the user's posture with the resulting avatar movement. Specifically, Figure 1 demonstrates the user's backward posture with the waist bending algorithm applied, while Figure 1 shows the forward bent posture and its corresponding avatar movement. These examples highlight the effectiveness of the proposed method in accurately tracking and replicating user movements within a VR environment.
That's cool.
This study proposes two hypotheses. H1, the estimation algorithm, upper body
Upper
tilting,
all
all directions
directions.
and lower body bending estimation, accurately tracks movements. H2, increasing the similarity and precision between the user's movements and the avatar's movements is expected to have a positive impact on immersion. To validate these hypotheses, we designed an experiment consisting of a phase to evaluate the accuracy of user and avatar movements, and a phase to assess the level of immersion. We then analyzed the effectiveness of the proposed method based on participants' survey responses. This study aimed to enhance the immersion and realism of VR systems while reducing the need for additional hardware. Second related work, accurate estimation of upper and lower body movements in virtual reality environments, is crucial for enhancing the user experience.
Yeah.
In particular, tracking movements using only a HMD and basic controllers holds significant potential for reducing hardware dependencies and lowering costs. However, this approach has several challenges, such as reduced tracking accuracy and diminished quality of the user experience. In this study, we review existing research that focuses on tracking user movements with only HMDs and controllers, and analyze the impact of the sense of embodiment and synchronization between the user and avatar on the VR experience. Research on the sense of embodiment. The sense of embodiment refers to the feeling that an avatar or virtual body is perceived as one's own in a virtual environment. This concept is pivotal in immersive interfaces such as virtual reality. SOE comprises three main components: a sense of self-location, a sense of body ownership, and a sense of agency, encompassing the psychological experience wherein users feel unity with their virtual body and perceive it as an extension of their real body. Research has shown that greater alignment between a user's real movements and those of their virtual body strengthens the SOE. For instance, in one experiment, participants reported significantly enhanced immersion and realism when hand movements in the virtual environment closely mirrored real-world movements.
That's cool.
Thus, congruence of physical movements plays a crucial role in enhancing the sense of presence in VR. Moreover, the SOE is a holistic concept that includes a user's awareness of body ownership and self-location within the virtual space. To enhance this, accurately tracking a user's physical movements through a virtual avatar is essential, and research suggests that first-person perspectives provide a stronger SOE than third-person perspectives. These findings highlight the importance of SOEs in making VR experiences more natural and immersive for users. Advancements in motion capture technology and VR headsets have further contributed to enhancing SOE. For example, the latest wireless sensors and AI-based motion analysis techniques can more precisely reflect user movements in a virtual environment, thereby reinforcing their sense of unity with the virtual body. Ultimately, this heightened SOE serves as a critical factor in improving the user experience in VRB synchronization between users and avatars. Body synchronization between VR users and their avatars plays a pivotal role in enhancing the sense of presence and reducing simulator sickness. This synchronization is a fundamental factor in helping users feel a sense of unity with their avatars in the virtual environment. When the discrepancy between the user's real movements and the avatar's movements is minimal, the user may not perceive or easily tolerate these differences. However, when the discrepancy surpasses a certain threshold, a phenomenon known as the self-avatar follower effect occurs.
That's very
In this
great
scenario,
avatar.
the user consciously adjusts their body position to reduce the gap between their physical body and avatar, attempting to align their movements.
Yeah.
Moreover, if the discrepancy becomes too large, it can result in a body semantic violation, significantly diminishing the user's immersion. For instance, if the avatar's hand or foot positions differ significantly from the user's actual body position, the user is likely to feel uncomfortable and perceive the experience as unnatural. Research has shown that incorporating avatars capable of accurately tracking user movements in a virtual environment leads to a significant increase in immersion. Similarly, higher levels of avatar realism have been found to deepen users' immersion and foster more positive social interactions in VR. Walk et al. Explored the impact of avatar self-similarity on male and female users, and concluded that higher self-similarity led to increased immersion, although the effects varied by gender. While the visual characteristics of avatars are often considered important factors influencing the user experience, some studies have suggested that their impact on immersion is relatively limited. However, no research has yet demonstrated that movement synchronization has an insignificant effect on immersive experiences. In fact, ensuring that the avatar's movements closely mirror the user's real actions is more critical than focusing solely on the avatar's appearance. Therefore, synchronization between the user and avatar is deemed an essential factor in enhancing the overall quality of the VR experience. See research on tracking user movements. Various methods for tracking user movements using only HMD and controllers have been proposed in previous studies. For instance, one approach leverages the categorical codebook matching technique to predict and simulate user movements, developing a model that uses upper body movement data to infer lower body movements.
Yeah.
Additionally, research has explored markerless systems, such as Microsoft Kinect's RGBD camera, to analyze human motion. Another method involves attaching sensors to the user's body to track the avatar's full body movements, utilizing inertial measurement units, including gyroscopes, accelerometers, and magnetometers, to capture
Extra
motion.
motion. Right.
This method allows the real-time tracking of body movements and offers the advantage of being relatively cost-effective. However, IMUs are generally prone to drift issues, which poses significant limitations.
That's
These
usually
approaches
limited,
often
so-
require additional hardware, such as cameras or motion capture devices, or complex computational resources, which can limit their applicability to real-time immersive systems. These constraints may degrade user experience or increase costs. Furthermore, full-body tracking using cameras can raise concerns regarding privacy invasion or hacking risks, as highlighted by recent studies and reports. Users may feel uncomfortable with such surveillance technologies. To address these concerns, some studies have proposed algorithms that estimate upper body movements without relying on cameras or artificial intelligence models. However, these methods only achieve 80% lower body movements, which were not addressed in these studies. The need for full body motion reconstruction in single-player experiences has already been clearly recognized. When users are fully immersed in VR, they are unable to see their actual environment or body, making the reconstruction of body motion even more crucial. In multiplayer games, real-time full body motion reconstruction becomes essential, because failure to do so can prevent users from interacting with others by rendering their movements invisible. Desai et al. Noted that visualizing a full body avatar in multiplayer applications significantly enhanced the VR experience.
Yeah.
The study by Enshid et al. Explores a locomotion-based control approach for UAV control, presenting a method for implementing a real-time control algorithm using minimal sensor input. Similarly, this study proposes a more efficient algorithm that simultaneously estimates upper and lower body movements using only an HMD and controllers. Our algorithm accurately estimates body movements in real time using only HMD data, without the need for additional hardware, thereby enhancing user immersion and improving cost efficiency. This approach meets the need for full body motion reconstruction while providing users with a practical solution for natural interaction and heightened immersion. Third methodology, this study proposes a novel approach for accurately estimating an avatar's upper body tilt and lower body movements using only the motion of a single HMD. Existing systems, such as meta-horizon avatars, have limitations where upper body movements are not reflected, leading to reduced immersion.
Yeah.
However, the study focuses on effectively reconstructing user movements using only HMD position changes, without the need for external hardware or additional sensors. The proposed method estimates upper and lower body movements by measuring the relative angle and vertical distance between the head rotation axis and the pelvis rotation axis, based on changes in the user's HMD position. This approach aims to minimize computational overhead while ensuring natural avatar synchronization and enhanced immersion, even in multiplayer environments with multiple participants.
That's cool.
0 equal to Arcos AB or A or B or. Figure 2. Comparison of user movements and avatar movements in Meta Horizon. The images on the left show actual user movements, while the images on the right display the corresponding avatar movements without upper body tilt tracking. The proposed estimation method analyzes the relative changes between the two reference points based on HMD movement. A. Define coordinates and set vectors. First, the key coordinates are defined as follows: He R3 position of the HMD, Re R3 position of the rotation reference axis, F Euro R3 front reference point, SAR3 side reference point. The vectors from the rotation reference point to each target are defined as in, these equations represent the direction and distance of the HMD, front reference point, and side reference point from the rotation reference point R. The visualization of these equations is illustrated in Figure 3. B. Calculate and apply upper body tilt angle. The angle between two vectors A and B is calculated as in Figure 3. Visualization of the defined vectors. Figure 4. Visualization of the avatar posture estimation model. The angle of with the front reference and S with the side reference are computed as in, the applied method is illustrated in Figure 4. Utrill spawns to 90 degrees with respect to the front and side references. The upper body inclination offsets are calculated as in. Finally, the avatar's rotation is represented using Euler angles, and defined as in, where and represents the original yaw rotation of the y-axis, and remains unchanged. Lower body bending estimation. Lower body bending is estimated based on the vertical displacement of the HMD. The bending degree B is defined as the difference between the y-coordinates of the pelvis reference point ρ and the HMD position high, as in, a higher B value indicates that the user has bent their knees and lowered their head. If the HMD position moves outside the predefined X and Z range within the trigger zone, inverse kinematics calculations for lower body bending. If B exceeds the predefined threshold, lower body IK is enabled to simulate realistic leg bending motion. The B threshold value is pelvis, where a specific point is used as the activation threshold for lower body IK. The overall structure of upper body inclination and lower body bending is defined as in lower body bending equal to B. Finally, the movement of the avatar applying this model can be visualized as shown in Figure 5. Illustration of the proposed method for estimating upper and lower body movements using only head-mounted display data. Shows the head rotation axis and waist tilting trajectory in a user with minimal leg bending. Depicts the same head rotation axis with significant leg bending, allowing for more accurate estimation of lower body movements. Fourth experiment design. To validate the algorithm proposed in this study, a comparative experiment was conducted against other estimation algorithms. We collected data using IMU sensors for evaluation and comparison. For benchmarking, we selected the rule-based upper body movement estimation solution by Han et al. And the Mokopi motion capture system. However, the solution by Han et al. Was excluded from the final comparison, as it does not estimate lower body bending motions and achieves only 80% accuracy in recognizing upper body inclination movements. Equipment settings and participants. Participants conducted the experiment while wearing a MetaQuest 3 headset. Since only the HMD's positional data was required, hand controllers were not used for hand tracking. As this study does not involve motion capture, inverse kinematics in Unity was used to simulate the movements of elbow and knee joints, and Unity assets from the Unity Asset Store were utilized for implementation. Upper body inclination data was collected using the Mokopi motion capture system. A total of 32 participants aged between 20 and 30 were recruited. Participants were categorized based on their VR experience. 14 participants had no prior experience with VR. 11 participants had used VR at least once before, and 7 participants used VR at least once per month. The experiment took approximately 60 minutes per participant. B. Experimental procedure. The experiment was conducted in 2 stages to evaluate the synchronization between the participants' actual movements and the avatar. The first stage measurement phase assessed how accurately the proposed solution reproduces upper body movements compared to traditional motion capture devices by analyzing MPU 6050 IMU sensor data. The second stage experience phase focused on evaluating immersion and embodiment by allowing participants to perform tasks using the avatar in a first-person perspective. 1. Measurement phase.
Yeah, first phase.
Participants performed an initial calibration using a HMD and Mokopi motion capture system while setting a neutral standing posture. After a brief adaptation period to ensure real-time synchronization between their movements and the avatar, participants performed the following predefined movements in response to given signals. 1. Forward and backward bending. Upon receiving the signals, bend forward and lean backward. Participants moved their waist forward and backward to induce upper body inclination. 2. Left and right bending. Upon receiving the signals, bend left and lean right. Participants tilted their waist left and right to generate lateral upper body inclinations. 3. Combined movement. Participants performed lateral movements while maintaining a bent posture and simultaneously executed knee bending movements to evaluate whether the avatar could naturally reproduce complex motions. Mokopi sensors worn by the participant. The red circles indicate the positions of the sensors attached to the body. 2. Experience phase. At the experience phase, participants wore the HMD and played 2 VR games, a dodgeball game and a limbo game in a first-person perspective, while remaining synchronized with the avatar in real time.
That's cool.
Participants were required to avoid in-game obstacles and perform limbo movements using only their upper body motions. This phase was designed to assess the synchronization accuracy of the avatar and the level of embodiment experienced by the users.
That's cool.
Figure 7. Left, the dodgeball game from the user's perspective. Right, a user playing the dodgeball game with quick upper body movements. Figure 8. Left, the limbo game from the user's perspective. Right, a user playing the leaning backward. After the experiment, participants were given a rest period before completing a standardized embodiment questionnaire by Peck and Gonzalez-Franco. This questionnaire was used to collect qualitative data on immersion and avatar synchronization. To mitigate fatigue, participants performed stretching exercises after completing the experiment. See measurement methods and data analysis techniques. In this study, the primary variable for evaluating participant movement accuracy is the upper body inclination data. A quantitative analysis is conducted using the root mean square error to assess precision. Upper body inclination is represented as an angle that quantifies the degree of forward bending. Since this motion can be expressed numerically, it is well suited for quantitative evaluation. Moreover, due to the nature of upper body inclination movements, mean per joint position error is not an appropriate metric for comparing joint positions. Considering this limitation, inclination data is adopted as the primary comparison metric in this study. Additionally, using tilt as a metric is advantageous for linear relationship evaluations through Pearson's correlation, providing an intuitive measure of visual movement. By using tilt, we can ensure more consistent data compared with other nonlinear variables, thereby minimizing the potential for distortion in the correlation coefficients. For these reasons, upper body tilt data were chosen as the primary variables in this study. 1. Questionnaire. During the experience phase, participants completed the standardized embodiment questionnaire by Peck and Gonzalez-Franco, designed to evaluate embodiment. While the original questionnaire consisted of 16 questions assessing appearance, response, ownership, multisensory experience, and body incorporation, this experiment utilized only 13 questions, excluding those related to tactile sensations. 2. Evaluate the precision of an action. To quantitatively analyze the accuracy of the movements between the actual motions and those of the avatar in the VR environment, root mean square error was employed to calculate the error. First, actual tilt measurements and avatar tilt measurements in the VR environment were collected. The mean square error was calculated as in, the root mean square error was then computed as the square root of the MSE. This calculation preserved the unit of error, with a larger RMSE value indicating a greater discrepancy between the predicted and actual values. Conversely, a smaller RMSE value signifies a higher prediction accuracy. This allowed for an assessment of the precision of the experimental results. However, to determine the error rate, the error percentage must be calculated as this value allows us to determine the error rate. Fifth, results. The following section presents the evaluation results of the proposed algorithm, focusing on its accuracy in estimating upper body tilt and lower body bending, and its impact on user experience in VR. The results are divided into two parts. The first evaluates the algorithm's precision by comparing the estimated avatar movements with the user's actual movements, while the second examines differences in user perception and embodiment when performing VR tasks using avatars driven by our algorithm versus those in Mokopi motion capture. These findings provide insights into the effectiveness of our method in improving avatar synchronization, enhancing presence, and increasing embodiment in VR environments. Table 1. Comparison of movement estimation errors between our method and Mokopi. FB bending refers to forward and backward bending movements, while LR bending refers to left and right lateral bending movements. A. Evaluation of the measurement phase. In this study, the accuracy of the algorithm was evaluated by calculating the root mean square error between the HMD-based estimation results and Mokopi measurements for each movement. The results are summarized in Table 1, revealing the following key findings. The proposed method achieved significantly lower errors compared to Mokopi and FB bending movements, showing a reduction of over 10 RMSE. This indicates that the proposed solver performs more precise estimations for forward and backward inclination movements. Similarly, in LR bending, the proposed method recorded significantly lower errors than Mokopi.
That's
The
cool.
multi-action results demonstrate that the proposed method achieved less than half the RMSE of Mokopi.
Yes.
This suggests that the algorithm provides stable upper body inclination estimation, even when multiple complex movements occur simultaneously. The high error rates in Mokopi can be attributed to the limitations of IMU-based systems, which do not incorporate joint constraints or detailed posture knowledge. In contrast, the proposed solver explicitly applies constraints on upper body inclination. Figure 9. Comparison of estimated angles between our system, Mokopi, and IMU ground truth across multiple trials. And lower body bending, making it more specialized for VR-specific fundamental movements. These results highlight that, unlike general-purpose IMU-based motion capture systems, the proposed VR-specific algorithm achieves lower errors in forward, backward, left, and right inclinations. This experimental outcome confirms our hypothesis H1. A reduction of over 10 degrees in error can significantly improve the alignment between the avatar and the user's movements in VR environments. This, in turn, enhances interaction immersion and user satisfaction. Overall, the evaluation of the measurement phase demonstrates that the proposed solver, specialized for VR upper body inclination and lower body bending estimation, significantly outperforms consumer-grade motion capture methods like Mokopi in terms of RMSE.
That's cool.
This result suggests that the method can contribute to making avatar movements more natural and
Natural and
accurate in
accurate
various
in
VR
various VR
applications.
applications. That's great.
B. Evaluating the trial phase. In the dodgeball game, participants successfully avoided an average of 74 out of 100 targets when using the proposed solver, whereas they avoided an average of 58 targets when using the Mokopi-based estimation. An independent samples t-test revealed a significant difference between the two conditions, f equal to 15.308, p less than 0, indicating that our solver achieved a significantly higher avoidance success rate. Performance comparison between our system and Mokopi in the dodgeball and limbo games. In the limbo game, participants successfully passed an average of 27 out of 30 limbo obstacles using the proposed solver, compared to only 13 obstacles when using Mokopi-based estimation. Statistical analysis confirmed a highly significant difference between the two conditions, t equal to 33.392, p less than 0. Additionally, a post-experiment survey was conducted to assess participants' perceptions of their avatar. The results showed no statistically significant difference between the two conditions in terms of avatar appearance, t equal to 1.6801, t equal to 1.70. Our solver was rated significantly superior to Mokopi. Our solver was rated significantly superior to Mokopi, feeling that their physical movements were more accurately reflected in the avatar when using our solver received more positive ratings. Furthermore, in terms of embodiment, our solver demonstrated a significantly higher level of embodiment. F equal to indicate that although the avatar appearance was perceived similarly in both conditions, our solver was significantly superior to Mokopi-based estimation in terms of response sensitivity, ownership, multisensory experience. Figure 11.
Embodiment.
Immersion survey results comparing the algorithm-applied avatar and the motion capture avatar across various factors. These findings may seem surprising, but they can be attributed to the use of consumer-grade motion capture equipment. While different results might be obtained with high precision, professional-grade motion capture systems, our target users are general VR consumers, making the comparison conditions different. Some participants reported that the motion capture felt slightly delayed, while others mentioned that they had to bend their bodies or knees more than expected. A deeper analysis of the motion capture data revealed that network transmission delays from the motion capture server and reliance solely on accelerometer-based position estimation contributed to accumulated errors over extended use. To mitigate this, Mocopi requires periodic recalibration. These factors likely explain why our solution outperformed the consumer-grade motion capture system, particularly in games requiring fast movements. Ultimately, the performance differences observed due to the limitations of consumer-grade motion capture systems could potentially be improved with more precise tracking equipment. Nevertheless, the high survey ratings for response sensitivity and embodiment demonstrate the validity of our H2 hypothesis. See impact of VR experience on performance. To investigate the influence of users' prior VR experience on task performance, participants were categorized into 3 groups based on their VR experience level: novice, intermediate, and proficiency.
Nice.
Performance evaluation was conducted using 2 VR-based tasks, the dodgeball game and the limbo game, by measuring the number of successfully avoided balls and the number of limbo obstacles successfully passed.
That's great.
Statistical analyses included the Shapiro-Wilk normality test and ANOVA. For the dodgeball game, the Shapiro-Wilk normality test results indicated that data from both systems satisfied the normality assumption for all VR experience groups.
That's good.
ANOVA analysis subsequently showed no statistically significant differences across the experience levels for both our system and the Mocopi system. These results suggest that prior VR experience did not significantly affect performance in the dodgeball task.
That's good.
Figure 12. Performance comparison in the dodgeball game between our system and Mocopi across different VR experience levels. The y-axis represents the average number of dodged balls. Similarly, for the limbo game, the Shapiro-Wilk normality test results indicated normal distribution for all VR experience groups within both our system and the Mocopi system. Subsequent ANOVA analysis also indicated no statistically significant performance differences between experience levels in either our system or Mocopi. This further supports the finding that VR experience has minimal influence on performance in the limbo task. Figure 13. Performance comparison in the limbo game between our system and Mocopi across different VR experience levels. The y-axis represents the average number of successful limbo passes. These results suggest that our proposed method provides consistent and stable performance regardless of prior VR experience. In both tasks, even novice users could achieve results comparable to experienced users without facing significant difficulties. One possible explanation is that both our system and the Mocopi-based motion capture fundamentally rely on the user's physical movements, thereby minimizing the influence of VR-specific experience. This explanation is further supported by the lack of significant differences observed across both systems. Consequently, it can be confirmed that motion-based VR tasks inherently rely on intuitive physical movements, rather than VR-specific skills or familiarity. Ultimately, our algorithm demonstrates significant potential for broad adoption in consumer-oriented VR applications, particularly due to its advantage of not requiring special training or expertise for effective operation.
That's good.
6th discussion. In this study, we proposed a method for estimating upper and lower body bending using only the HMD of a VR device. Although this approach may result in lower accuracy compared to other methods, it offers significant cost savings. Section VA discusses the differences and advantages of the proposed method compared with traditional movement tracking approaches. Section VB outlines the directions for future research. A application of the proposed approach. With recent advancements in VR tracking technology, various methods have been proposed for estimating user movement. Many previous studies have focused on achieving high accuracy using motion capture systems or IMU-based tracking, which often require additional hardware and significant computational resources. However, such approaches may not be practical for consumer-level VR applications, where accessibility, cost, and ease of use are critical factors. To address these limitations, we propose an HMD-only algorithm that estimates upper body tilt
and lower body. That's cool.
bending without the need for external tracking devices or computationally expensive AI models. This approach enhances motion tracking efficiency while significantly reducing the hardware and processing costs for both users and developers. The experimental results demonstrate that our proposed system provides a more immersive and natural user experience compared to conventional consumer-grade motion capture systems. Participants rated response, ownership, multi-sensory experience, and embodiment significantly higher when using our HMD-only tracking algorithm. The statistical analysis showed significant improvements in ownership, multi-sensory experience, and embodiment, confirming that the proposed method enhances the user's sense of presence in VR.
Yeah, that's good.
Unlike conventional motion capture systems or IMU-based tracking, the proposed method estimates upper body tilt and lower body bending solely from HMD positional data. This eliminates the need for additional sensors, reducing the complexity and computational overhead associated with motion tracking. The proposed method proves particularly beneficial in multiplayer VR environments, where simultaneous real-time tracking is required for multiple users. Traditional motion capture devices significantly increase costs, while camera-based tracking solutions suffer from occlusion issues and potential user discomfort. In this context, our HMD-only approach serves as an effective, low-cost alternative, offering hardware-free and resource-efficient motion tracking for various VR applications.
Good.
B. Future research directions. Our study successfully estimated upper body inclination and lower body bending with minimal cost and technical requirements. This suggests the feasibility of avatar tracking research at a low cost, while also paving the way for future studies in the following directions. Although our method accurately estimated upper body inclination, it did not account for upper body rotation to the left or right. There are fundamental limitations in estimating a user's upper body tilt and orientation using only an HMD. Since an HMD tracks only head movements, it may not always correspond precisely to the movement of the actual torso. In particular, attempting to directly infer yaw rotation from the HMD is unreliable. When a user turns only their head sideways, their head direction and torso direction may differ. If this distinction cannot be made using HMD rotation data alone, significant errors in upper body orientation estimation may occur. In fact, a VR inverse kinematic study pointed out that determining shoulder-torso orientation based solely on head rotation resulted in large errors when users looked sideways, ultimately leading them to abandon this approach. Thus, treating head yaw information as a direct representation of upper body rotation is only viable in limited conditions where the user is facing forward. However, it is unreliable in general scenarios where users turn their heads. While our study was conducted using only an HMD, future research will explore methods to estimate upper body rotation by incorporating hand controllers. Additionally, while our current method estimates lower body bending, it does not account for user locomotion, as it falls outside the scope of the study. However, building upon our findings, future research that incorporates user movement data collection and analysis could lead to the development of a comprehensive full-body motion tracking system that considers user locomotion. 7th limitations. During the user experience evaluation, some participants exhibited a tendency to bend their spine into a C shape when performing upper body tilt movements. As a result, spinal bending was incorporated into motion estimation instead of pelvic tilt, leading to inaccuracies in the estimation results. Additionally, we observed that when users performed upper body tilting movements, they tended to shift their hips backward and bend their lower back to maintain balance and prevent falling. This issue cannot be resolved by our current solution and highlights the limitations of our proposed algorithm in handling complex upper body movements. Furthermore, we did not conduct evaluations in a multi-user environment due to the numerous factors that need to be considered in such settings. Multi-user interactions introduce additional challenges, such as synchronization, collision handling, and latency, which require careful design considerations.
Yes.
Given these complexities, we plan to address multi-user scenarios in future research to ensure that our approach remains effective and applicable in shared virtual spaces. 8th conclusion. Tracking user movement using only an HMD, without external hardware, remains a crucial challenge for enhancing accessibility and reducing costs in VR applications. Current solutions either demand significant computational resources or rely on additional tracking devices, limiting their practicality for widespread use. Despite these approaches, achieving accurate and natural motion tracking with minimal hardware remains an unresolved issue.
Yeah.
To address this, our study proposes a method for estimating upper body tilt and lower body bending using only an HMD, eliminating the need for external hardware or computationally expensive processing. Our evaluation, which included both quantitative accuracy assessments and qualitative user experience feedback, demonstrated the feasibility of our approach. The results indicate that users could effectively interact in VR without noticeable motion artifacts, and our method provided an immersive and intuitive experience. Additionally, accuracy evaluations confirmed that our system successfully estimated user movements while maintaining low estimation error rates, reinforcing the reliability of our approach. Furthermore, our statistical analysis revealed that prior VR experience had minimal influence on performance, as novice users performed comparably to experienced users. This suggests that our system offers intuitive usability, making it accessible to a wide range of users without requiring prior training. However, our method does not fully capture all degrees of upper body rotation and fine-grained lower body movements, which may limit its applicability in highly dynamic VR interactions. Future research will focus on extending the motion tracking range, integrating additional contextual information from hand controllers or AI-based predictive modeling to enhance full body motion estimation. Fifth, will further advance the potential of HMD-only tracking, making it a more versatile and cost-effective solution for consumer VR applications. Acknowledgement. This research was supported by Kumo National Institute of Technology. References J1.
Okay, you can see all the references. I will not read from her, the AI assistant. Sorry. So you can see, you can read all the references. I will provide the link in the description, and I can read about the authors. Start from here.
Jemin Lee is currently pursuing the bachelor's degree with the Department of Computer Software Engineering, Kumo National Institute of Technology, Gumi, South Korea, specializing in extended reality and metaverse technologies.
That's great.
His research focuses on enhancing immersion in virtual reality through computer graphics and providing lifelike experiences for VR users by detecting and estimating human behavior.
That's great.
Jongyan Kim is currently an undergraduate student in the Department of Computer Software Engineering at Kumo National Institute of Technology, Gumi, South Korea, specializing in extended reality and metaverse technologies. His research interests include gaze tracking and multimodal interaction. focusing on combining gaze, speech, and gesture to create intuitive user experiences in extended reality applications for the manufacturing and defense sectors. Youngwon Kim received the BS degree in Computer and Communication Engineering and the PhD degree in Computer Engineering from Korea University, Seoul, South Korea, in 2012 and 2018. From 2019 to 2023, he was a senior researcher and team leader at the IT Convergent Systems Research Center, Korea Electronics Technology Institute. Since January 2024, he has been a professor in the Department of Computer Software Engineering at Gumo National Institute of Technology, Gumi, South Korea. His research interests include extended reality, human-computer interaction, virtual reality, artificial intelligence, and the
Doesn't matter.
metaverse.
That's really good. That's really good. So these are the great authors. I have introduced you to them, to yourself. Okay, going to summarize this paper now. Okay, fine.
Overview of head-driven motion estimation. Research objective. This study, authored by Jaemin Lee, Jungyeon Kim, and Youngwon Kim, introduces a novel, cost-effective algorithm designed to estimate upper body tilt and lower body bending in virtual reality environments using only a head-mounted display.
That's great.
Core methodology. The proposed method calculates the relative angular and vertical displacement between the head rotation axis and the pelvis reference point. By analyzing these spatial vectors, the system accurately reproduces user postures without requiring additional sensors, external cameras, or expensive motion capture hardware. Experimental design. The study utilized a two-stage evaluation, measurement phase. The algorithm's precision was benchmarked against the Mokopi motion capture system by calculating the root mean square error of inclination data during specific physical movements. Experience phase. Participants performed 2 VR tasks, a dodgeball game and a limbo game, to evaluate subjective metrics such as embodiment, response sensitivity, and overall sense of presence. Key findings and results. Superior accuracy. Experimental data showed the proposed algorithm significantly outperformed consumer-grade motion capture systems, achieving a reduction in RMSE for forward, backward, and lateral bending movements. Enhanced user experience. Post-experiment surveys revealed that participants felt a stronger sense of ownership and embodiment when using the HMD-only algorithm compared to the alternative system. Accessibility and consistency. Statistical analysis confirmed that performance levels remained consistent across different user experience groups, indicating that the solution is intuitive and requires no specialized training for effective use.
Yeah.
Practical implications. By minimizing hardware requirements and computational overhead, the algorithm is particularly suitable for multiplayer VR applications where efficiency and accessibility are paramount. Current limitations and future scope. Constraint challenges. The researchers identified difficulties in tracking complex movements, such as spinal C-shaping or horizontal torso rotation, which the current HMD-only approach cannot fully resolve. Expansion plans. Future research aims to incorporate data from hand controllers to improve rotation estimation, and to develop full-body tracking modules that integrate user locomotion, further enhancing the realism of virtual interactions.
That's good.
Contextual summary. The research provides a compelling solution for the limitations of current VR motion tracking, specifically addressing the need for cost-effective high-immersion systems. By demonstrating that sophisticated tracking can be achieved through HMD data alone, the authors provide a scalable framework for future XR developers. The study effectively bridges the gap between complex hardware-dependent systems and the need for inclusive, user-friendly VR technology, proving that specialized rule-based algorithms can significantly improve the sense of presence for general consumers while maintaining high levels of accuracy and performance in dynamic virtual environments.
That's really great. So I summarize the paper, and you can also do the quiz also. Number of questions you want to make, you can make it. I'm currently using Speechify as a AI tool for reading it, for summarizing it, and for creating questions. Okay. Based on number of questions you want to make, suppose I want to generate 10 questions, I can generate and generating quiz, question number 2 of 10, question number 3 of 10, all the questions will generate very soon. And then I can answer each question. It can, okay, for tracking body movements. I means head mounted for tracking body movements, external motion capture sensors, RGBD cameras, head mounted display. Head mounted display. That's correct. What specific movement does the proposed algorithm estimate? Finger. Hmm. That's great. What is the primary benefit of the proposed algorithm? In multiplayer environment, it allows user to teleport within the game. or it eliminates the need for interconnectivity, utilize limited computational resource efficiently to increase the screen resolution for all users. On the proposed algorithm in multiplayer environment. Third option is correct. Computational. It utilizes limited computational resources efficiently. Okay. What does the sense of embodiment SOE represent in VR? The ability to interact with real world objects, the feeling that a virtual body is once on, and the resolution of HMD display, the speed of no, the feeling that a virtual body is once on. Okay, sense of embodiment. Bravo. What is the self-avatar follower effect? A game mode where avatars chase each other. The avatars automatically following the user's gaze. A user adjusting their body to match an avatar movement. An AI-driven pathfinding algorithm. Avatar automatically following the user's gaze. Self-avatar follower effect. A user adjusting their body to match an avatar's movement. Third or second option may be correct. The avatar automatically following the user's gaze. User's gaze, I don't know. Self-avatar. A user adjusting their body to match an avatar. Yeah. What metric was used to evaluate the precision of the proposed algorithm? Root mean square, frames per second, precision of the proposed algorithm. Root mean square error. How did the proposed algorithm perform compared to Mokopi motion capture system? It showed lower RMSE indicating higher precision. Okay. Uh, the performance was identical. It was significantly less accurate. It had higher error rates in all tests. So it showed lower RMS indicating higher precision. ठीक है? And that's good. Perform compared to Mokopi question captures. Which game did participant play to evaluate embodiment and synchronization? First person shooter and dodgeball game to evaluate embodiment and synchronization. What is one limitation mentioned regarding the current algorithm? It requires too much electricity. It's too expensive for average consumer. It can only be. It does not account for upper body rotation. Yeah. Regarding the limitation, it does not account for upper body rotation. Yeah. Last question. Let's see. How did prior VR experience affect performance in the task? Experienced user performance significantly better. Novice users were faster than experienced user. Users struggle to understand the controllers. Experience had minimal influence on performance. So novice users were fast. Experienced user perform significantly better. Understand the control. Affect. How did prior VR experience affect performance in the task? Experience had minimum influence on performance. Novice users were faster than experienced users. Novice users struggle to understand the controls. No, it depends on all novice. Novice perform significantly better. First option. Let's see. Oh, incorrect. Experience and minimal influence on performance. Okay, 90% correct. Awesome. Awesome job. Yeah, nailed it. So you can generate many questions. New question you can generate. Make as much questions you can make to understand the paper better. Okay. Okay. So it's time to end now. You can use this tool. Great tool. Speechify. So I'm going to end this video now. Thank you so much. Okay. You can use this great tool, Speechify, app.speechify.com. You can go there, and I will also provide the link of this app. Just download it or use in your web browser. And I'm currently using in the web page format. You can see app.speechify.com for reading it. Okay, for making summary, making quiz, understanding as much as possible, making the paper reading more effective. Okay, and you can also generate podcast. Just write the podcast, which language you want to, Hindi, English, and any language you want, Korean, Malaysian, Netherlands, anything in your language you can create a podcast and understand in your language. If you're not able to comfortable in English, you are not native language is not English, so you can create your podcast and understand the paper very well. Okay, that's a great tool. And in which type of uh, lecture mode, storytelling, late night show, in whatever type you can create that. Okay, so it's time to end now. Thank you so much.